So welcome everyone to this month's ISSC seminar series. Today we'll have two talks from Mickaël Rigault and Josh Speagle, and we'll cover a nice combination of simulation-based inference and software package that Mickaël is going to tell us about. Mickaël, do you want to get started?
Okay, well, thank you very much for the opportunity to show you that. So it's actually the first time I'm presenting a software I've been developing, because it's usually not the right audience, but I'm pretty sure you are. And so the goal of this package I've been developing is to help people simulating how targets are seen by surveys and how surveys can introduce bias or introduce selection effect and how you can recover those, and as well as how complex and trying to build very complex targets if you want to, or very simple ones. So the concept is quite simple. It's something you may have seen in other packages before, and in the famous SNANA that's been used quite a lot, I think, in LSST. It has been developing by Kessler for a while now. And so this skysurvey aims at, I don't know if it's replacing is a good word, but being something similar to what the step one of SNANA is, that is simulating transient as they would be seen by the survey. And so if you know SNANA, this does not include the beam-induced bias correction or the cosmology fitting part. This is outside of it. This is just focusing on how you can create complex targets, how you can create any kind of surveys, and how then your survey can observe these potentially complex targets. So you have to build the targets, and when I'm saying targets, I mean the true objects as they are in the sky. And the survey will be basically your list of observations, so what you have observed when, with which filter, what sky conditions, and so on. And then the code itself is going to have very simple tools that enable you to build a data set. And what I'm calling a data set is basically the light curve as you would observe them with noise and so on. And so the goal is that any targets you want to create, you want to have access to those parameters, you want to draw the true spectra, the true light curves, or anything you want. And the surveys, you may want to have summary statistics from the survey, such as the cadence it has, or how many times it has observed in the G-band, for instance, or something like that. And you want to be able to say, okay, if I give you any coordinates to the sky, give me the logs of observation as to these coordinates to the sky. And it's usually what you need when you want to do light curve from the targets. And the data set is the thing that's going to combine those two things, and it should be effortlessly done. And the goal is that once you have this big data frame, you want to be able to get realistic light curves. So this would be exactly the light curve that you observe them. And from that, you want to derive rates or simulate selection function, and you want to complexify the difference between what the observation should be and what your observation truly are, given some signal to noise cut you want to do, and so on. And so the goal is that skysurvey is able to do all of that very easily. And so here I'm going to show you some screenshot of the lines of code that lead to that. And so for instance, if you want to get a survey, you just need to do, I don't know if you see my pointer, but
yeah, I can see it.
Yeah, the goal is that basically you import skysurvey, and then you have a list of a lot of pre-built targets. For instance, this in 1.8, this is my field. And then you load it from a from-draw method that draws 10,000 of those targets up to redshift of 0.1, 0.3, and from a given time range. It happens that if you don't provide the number of supernovae you want, it's going to draw following the volume limited the volumetric rates of the supernovae, and so this would be, I don't know, hundreds of thousands, for instance, yeah, up to 0.3 for 2 years. Then for the surveys, so this is an example of the survey I'm working with, so ZTF, which is the precursor of LSST, if you don't know yet. And so this, I have lots of observations, I have the collection of things I know. And so I have developed a few different surveys, like DES, for instance, or LSST is on the way. And you have those from logs, but you can also provide, and I'm going to show you an example after that, directly exactly the logs they are. And so you can load from data and not from log. I'll show you. But what is interesting is that once you have those two things, a 1A, or any kind of transient, and a survey, like for instance ZTF, the only thing you need to do is to call this object, which is called a data set. and has this class method that basically is creating the data set from a target and surveys. And actually the target here can be a list of targets if you have several of them. And that's it, and it's going to work. And it's going to give you a table. And so the target, all of that is, so because the goal is to have something easy to be used. So it's using the standards of the Python environment. And so for instance, all the data are stored as data frames. And so for instance, the data for the 1A, you have all the parameters you may know of for supernovae. So the stretch, the color, the Milky Way extinction, for instance, or the observed magnitudes. For data sets, this is what actually defines the data sets. It's just the data that's contained, so again, the 0 point sky noise, when you observed which band, the coordinate of where you're pointing your telescope, and the field ID, because ETF is not a random pointing, it's following a grid system, so this is a grid number. And once you have those two things, then you see that your data set, the data you observe will just be a multi-index data frame that has as one index the number of the supernovae, and as a second index, the number of the index of the survey associated to when the survey has observed this target. And then you have the light curve that is here. You just need to do a .xs, the number of the supernovae, and you have the light curves. And so all of that is quite fast. I mean, this merging here is extremely fast, and this is actually the big net improvements that have been that happened for in comparison to other simulation survey, like I don't know if you know SIM survey or SNSIM, for instance. Those are other kind of somewhat similar simulator, or even SNADA. The fact that the back end behind that is the GeoPanda spatial join that makes this combination of those two things extremely fast. And so this is where the magic happens. It's not me who got it that, but we are making use of it, the GeoPanda spatial join. So at the end of the day, it looks like that. So you have targets, you have a survey. For instance, here the ZTF survey contains 40, this is 2.5 years of ZTF, and this contained almost 50 million entries, which corresponds to almost 800,000 single exposure. And so you have more entries exposure because ZTF it's a 64 by 64 readout channels. And so it's a complex camera like LSST is, for instance. So here you have the data frame associated to this observation, and this will be the light curve of one of our random supernovae number 347, sorry. This is the light curve you get, and this is a typical ZTF light curve. And you see it has noise, and this is because this is the noise of your measurements. So the goal of skysurvey is that it's fast. And so in that case, for instance, loading a target, this is like takes no time, less than a second. Loading a survey, it takes 1 second because it's just basically opening a data frame, a very big data frame, but it's just opening a data frame with Panda. And the joining, and this is where the magic comes from, the joining and the light curve generation takes only 1.5 minutes. And so here is some benchmark I've been doing. And so you see that it's linear increase as a function of the number of targets. And the blue curve here is a full ZTF footprint over the 2.5 years of my logs I've been using for this example. If I were to just use 1 year, it would be this. And interestingly, if I were to use just the full 2.5 years, but over a small part of the sky, it would be very fast. It will load 5,000 type 1 supernovae in this part of the sky in less than 5 seconds. So it's extremely fast. It's faster than SNADA, for instance, for the same comparison. And the good thing with being fast is that you can test many things with that. And yeah. And so I have more examples of how you can change the things after that. But just so a quick recap of what the goal is that skysurvey is object-oriented, and like most of SNLR, for instance, I've been using a lot this reference because it is a reference. It is PIP installable, and it's fully modular, so you can, everything I showed you, you can change that and you can interact with it. And so the front end is like the data frame system, and the back end, the thing you're using to generate the light curve and the template and everything, this is based on SN Cosmo, which is also a reference of the field. Okay, so you can click here. This is a shortcut, a link to the documentation if you want to have access to that. Okay. So now it's how you can build your own survey. And then the next session will be how you can build your own targets. And so you don't want to use ZTF, most likely. You may want to use your own survey. And I know that this tool has been made, is used to simulate how, for instance, ultrasat may observe the sky, or we've been using it to understand how we can play with LSST on some small project we have at Lyon. So the concept is quite simple. You use Shapely. I don't know if you know Shapely, but it's a Python library for any geometry any geometry you want. And so you can use Shapely you have to use Shapely to build your footprint. And so this will be basically the polygon defined by the footprint of your camera in the sky. And so you, for instance, a simple circular or square footprint, but it could have any shape, or it could be any random polygon. It could also be a multi-polygon, and this is more what a modern camera looks like, for instance. And so, for instance, the ZTF one I was showing you, it's a 64 by 64 such multi-polygon. And I've been, for small project we are starting, I've been adding the simple version of the DS camera or the SST camera, which are not just the multi-polygon, but the contours of the polygon. So this will be useful to know how Lightcurve would look like, but it will not be enough if you want to include how gain variation play a role in the Lightcurve system. So once you have defined your footprint, so you see here, it's a footprint. You lost my pointer. So this is a footprint here. And then you need to define the data frame that basically provides the observing logs. Okay, so you need to provide the area index, so where the camera pointing. And so this is where the center of the polygon pointing in the sky. So this is the center of the camera. When, with which band. And so this has to be a band system known by SN Cosmo. So it has pre-built a lot of band, and it's a one line of code to add a new band if you have your special band. You need to know the sky noise in unit of the 0 point and the 0 point of your image. That possibly provides depth. You can get that from managed limit, for instance. And the gain is used to convert to have accurate measurements of the noise. And so once you have that, you see here on the right, you have the full extent of what you need to build a survey. So you need to provide a footprint. So here in that case, it's a simple circular aperture of a radius of 2 degrees. And then I've simulated 100,000 observations. It would be like an LSST, like I think 1 year of observation or something. And then I provide some random numbers. So I randomly draw the sky noise, the MGD, the band. So this is non-realistic because I'm randomly drawing in the sky, but it gives you an idea of what you can do. And then to create a survey, you just need to do this. You from pointing and you provide the data, which either are the simulated random, not realistic data frame, like this is a dict, but it's converting data frame inside the code, and the footprint. And once you have that, you have everything you need. You actually may have your own logs, for instance, if you have a survey that you knew already. So you just need to provide the footprint and you just need to load the data frame. In that case, it's just the same thing as here for my example. And you're going to get a survey, same way, okay? So once you have that, then your data are, as I showed, stored inside survey.data. And what you look in the sky, in the example I draw, it would be just this. So this is, in that case, when you draw from a random pointing in the sky, then the logs are converted as pixels. And so this actually, if you run it this way, loading a survey takes about 1 minute for 100,000 pointings. It's a time to associate each of the entry to the ILPI cell. And the definition of the ILPIX, so here is N200. You can refine that as much as you wish. So this is for any random pointing surveys. It happens a lot that you don't point your telescope randomly in the sky, but you follow a grid system. So this is the case for ZTF, for instance, that has a grid system to cover the whole sky. But it's also the case for DES, for instance, or the LSST deep fields. You know exactly the name of your field and you know where you're supposed to point. So you may have some from jitter, but you know where you're supposed to point. And so you can simplify a lot survey and fasten a lot of paths if instead of just saying all the time the same area index, you provide the field coordinates. So for instance, in that case, you provide a footprint, you define where the field system, how the field system works. So you provide, for instance, in that example, the name of the fields, so C1, C2, C3, and the coordinate of those fields. And then you do the same thing as before, except that you don't provide the data frame era and deck, you just provide the name of the field. So in that case, I just randomly draw from the keys here to randomly draw in the sky. And when you create a survey, the only difference is that instead of loading a survey, you just say that it's a grid survey. And so in addition to have just data, you also need data and the era and deck coordinates. And once you do that, for instance, in that case, it's the example for DES. It shows where the fields are in the sky. And in that case, I don't need to use ILPI anymore. I just can directly use Shapely and the geopoint association to know where a point is in the sky. And this means that basically loading the survey, instead of taking 1 minute, takes no time, take like, I don't know, a quarter of a second or something for the same number of entries. So this is very useful, but once it is loaded anyway, the survey will look the same way. It will be transparent for the rest of the code. Either you're working with a grid survey or the survey, it will be the same. Okay, so now you know how you can build your own surveys. And if you have something complex, like, I don't know, you want to play the game with how your detector or signal to noise is working, for instance, the background noise, if you want to say something about the gain, or if you want to say something about I swallow the name, any detector defect you may want to imagine, then this will only reflect on sky noise that can be depending on where you are in the sky, in the footprint and so on. So this, at the end, is all summarized to this in Sky Survey. You just need to convert whatever number, whatever name you want in this. If you want something more complexified, we can work on that. But so far, I think most of the use case can be summarized to this idea, these keys. Okay. So now concerning the targets you may want to use, you have pre-built a few targets like the 1As, any time series you can find from SN Cosmo. So for instance, is a name and you have like hundreds and hundreds in SN Cosmo that are pre-built. We have developed the kilonova because this is quite used nowadays. And there is top level collections of transients that are pre-made like the type 2, the type 1b and so on. And all of them will look the same way, except that the parameters will vary. So for instance, the 1A has the X1 and the stretch and the color and so on, while time series or don't have that, they just have a T0 and absolute magnitude and so on. So you can change all of the parameters you see here, so how they are drawn, the rate, the redshift, and so on, as options from draw. What is interesting is that it's the way the transient is built. So this is actually creating a DAG. So this is its own independent package that SkySurvey is using, it's modeldag. And so the way it's working, and this is a direct screenshot from the doc for modeldag, is that you provide a dictionary that has a key that is, and you explain with the function keywords and the quark keywords how this parameter is drawn. And then the data frame is built one key at a time, and you can refer to a key already drawn by just using the @ name here. So for instance, in that case, I'm going to draw A from a normal distribution, and the errors of A will be drawn from this random function here. And the value I'm going to use is actually the A I drawn already. So this is going to create a DAG like that, and you can complexify this as much as you wish. So for instance, this is a screenshot of how a 1A model look like. And so for instance, in that case, I'm drawing a redshift, I'm drawing the stretch for whatever function, the color and so on. But you see, when I want to draw the absolute magnitude of a 1A, I need to input the stretch I already draw here and the color associated to this target here. And in that way, it's going to be self-consistent. And it's going to create this DAG like that. And the code will simply will draw one at a time and will know in which order it has to draw that. And it's going to draw that. And the good thing is that you can complexify now the model very easily. So for instance, in that case, let's imagine I want to not have a single beta parameter. So this is a connection between the stretch and the magnitude of supernovae. But I want this to be a collection of values that potentially vary as a function of whatever. I can just have beta to be drawn from a normal distribution. And now in the absolute magnitude, I just need to say that beta is depending on the absolute, on this beta that I draw already. And in that case, you see that the only thing I need to do is to change my model by adding this extension here. And then the model will update that and include this. And it will work. Okay, so that's the conclusion. I've been a bit slow, but this is to advertise that you can use SkySurvey. Hopefully, it's going to meet your needs. And I'll be happy if you have some use case I haven't thought about. and it's under development, and here it is. Thank you very much.
Awesome. Thank you so much, Mickaël. We have time for a few questions. Feel free to raise your hands if you have questions for Mickaël. I'll ask a quick one to get started. Super interesting, your previous slide, you were showing that you're essentially building some sort of probabilistic programming language here. And are you relying on an external system, or are you yourself then interpreting this DAG and sampling the random variables in the right way?
Yeah, so exactly. So it is very simple in the sense that you see. So I was looking for that for a while, and I haven't seen it on anywhere. So I wanted to just build a DAG, so just something that can build a DAG from a dictionary just by simple things. So this is something I built from scratch. And for the drawing, I'm relying on GraphViz and other libraries like that, but just for the drawing. And you can convert that to GraphViz or NetworkX, for instance, the DAG I'm creating. But the idea is that, I wanted to work in something as simple as a dictionary for people to be able to use that and without have to need to understand the graph system and anything. You just need to know that if I want this, I just need to know that I'm using the X1 I get from there. And this is how you provide that with this add stuff. Right. And this is the only magic that is in there. So I invite you to look at, I don't know if you see that, but if you can just look at this in the, and it's very simple. And basically for the function you can draw, it has the example of kind of function you can build in your tag. It's quite simple.
Very nice. Cool, thank you. I didn't know this package.
It's quite new. I just made that for that. It used to be part of skysurvey, and now it's just a standalone.
Nice. Okay, cool. I see that Casey has his hand up.
Hi. Can you hear me?
Yes.
We can hear you. Yeah, I sound weird because these are voice casts. Okay. Anyway, thanks for your talk. I was curious about how the selection effects and selection function is encoded, because as you know, like there's in a survey there's photometric selection that you detected, and then there's also, well, did anyone get a spectrum? And there might be various rules about how many detections you need on a light curve to declare that it's detected. Is that how is that implemented in this?
So it is not implemented in a sense that the goal is that you're going to create the line curve of everything you asked for, and then you're going to have a huge data frame with everything on it. And this is where the skysurvey is supposed to stop. So then the selection function is up to you to define. Either you work on the true parameter if you want to, but you don't have access to that in real life. But you can, because you have access to those. Or you work with, you have the light curve of every object, like, I cannot go up. You have the light curve of every object, like, for instance, I don't know, where is that? Here, for instance. So you have the light curve of every object, and then it's up to you to define your criteria. You can group by, you can select your signal to noise minimum you want, and you want to say I need at least 4 of them before the maximum. So I had triggered a spectrograph or something. So it's up to you to define then how you will do your selection function. The skysurvey on itself, with the current version it has right now, the goal is to provide the light curve as they are. And so I have cases in this type data frame here where there is none of them that has signal to noise greater than 1. But you have a shitty light curve, but this will be the realization of it. And then it's up to you to say, okay, this one should be discarded because it never reached my minimum 7 points per light curve or something. And so I've been working on creating a goal. An end goal will be a skysurvey environment where basically you have skysurvey extension, like you have a Flask extension, if you know this Flask package. You have many extensions, and so one of them could be skysurvey selection function, where you can have inside pre-built selection function that are already in SNR, for instance. And then people can add up stuff on it, like what will be your mask you want to apply to data sets that should look like an SNLS survey, for instance, or an DS survey or whatever. But it's up to you. So I'm trying to unlike SNR or many packages, I'm trying to confine exactly what skysurvey is supposed to do. If it's flexible to create survey you want. You can build very complex nature of transients. This is where I'm focusing more. And then you're going to create light curves. And then that's it. I used to be able to fit the light curve, and I think I removed that from the, because it doesn't need to. It's something else.
Yeah. Thanks.
Do we have any other questions from Mickaël? I don't see a hand up. So thanks again, Mickaël.
Thank you very much for your time.
Could you send us your slides so that we can link them afterwards?
Sure.
Cool. Thank you. And so now we can switch to Josh.
All right, let me make sure that my screen comes through here.
We can see it.
Okay.
Yeah.
Okay.
Yeah, go for it.
All right. Okay, so we're going to switch gears a little bit. I think, yeah, Mickaël's talk is going to be perfect because I think it really outlines the sort of previous side to everything that we'll talk about. So Casey just mentioned selection functions. And so this is really going to be talking about the modeling side for lots of these types of input data. So for those of you who might not know me, I'm Josh. I'm a professor of assistant professor of astrophysics, joint between statistical sciences and astronomy and astrophysics here at the University of Toronto. And a lot of what I'll be talking about today is kind of the flip side of how we can incorporate uncertainties into machine learning methods and sort of the current place we're at, which we call SBI++. I'll sort of try to explain where those things come from and what sort of the methods we're looking at. So the motivation for what got me into this is that I, as sort of someone with a more statistical background, I've always been really, really keen on trying to find better ways to incorporate uncertainties into the actual modeling process. And these come in all sorts of forms. So this is very general. And we know that these will have an impact on downstream, ML focused applications. So the question, of course, is how much, right? How much do we have to worry about the impact of uncertainties in theory and practice? And how do existing methods either implicitly or explicitly deal with these? A lot of methods essentially amortize over the distribution or of uncertainties within a population. And are there easy strategies to incorporate errors into existing methods if they don't? And in particular, the type of applications in astronomy that I'm really focused on are cases where we have a lot of training data which have very different, essentially, population distributions and signal-to-noise distributions than we are hoping to apply them for in application. So, for training on really high signal-to-noise spectra or nearby objects, we're trying to really extrapolate to, much lower signal-to-noise, much further away objects. How do we guarantee that our method's going to behave in sort of a sensible way as we extrapolate in a very specific way to that type of out-of-distribution data? So that's essentially what I'm sort of thinking about in terms of astronomy. And so really, the setup is the same as we just discussed from skysurvey, which is that you have some parameters, you're going to get some true data, and then you need to add some observational effects, either from the survey, from something you know. And what we actually train on, of course, is the thing at the end, right? That's what we're using to do some selection or using to train some machine learning model. And there's some noise process involved in this that we maybe do or don't know explicitly. And therefore, if we want to do a good job extrapolating to these types of very faint out of distribution data, we need to have some way of dealing with these types of censorship processes or selections. And we really need to have a model that's working on the true data here. So that's going to be sort of what I'll be driving at, is how do we get a model that learns from the observed data some underlying parameterization, either latent or explicit, for the true data. And once we have sort of some knowledge of what this distribution might look like, we can then use different noise processes, different selection functions to generate different sets of predictions that we can then use to do inference. So that's the main idea. So the workflow for most machine learning applications kind of looks like this, right? We have some set of observations, we have some set of targets, and we're going to sort of get there by coming up with some function. So which I just wrote down here is kind of f of y given x and phi, where phi is going to be all the hyperparameters of our machine learning model. And we often optimize over phi, although we can also marginalize over phi. But I'm not going to talk as much about sort of dealing with the hyperparameters of a machine learning model in this talk. So I'm going to assume that we essentially have fixed these and we're using a fixed model. We're trying to optimize a particular model in order to generate a prediction. So it's important when we talk about uncertainties in this context and sort of what types of uncertainties there are. And I like to just think of them in sort of 4 groups. We have uncertainties on the inputs, and that can be both the observables, which I'll call X, as well as the targets, which I'll call Y. And we also have uncertainties on the model, and that can be uncertainties on the hyperparameters of the model. And it can also be uncertainties on the predictions from the model. In other words, if the model not only predicts a particular result, but also predicts some uncertainty around that result. And that can either be, you know, some sigma. I sort of use SY as a shorthand, but it could also be a full probabilistic distribution. And so for this sort of discussion here, I'm going to be mostly ignoring this one and focusing instead on the other 3, which are mainly related to the things that we are sort of comparing to. So the example that I want to motivate for this, for some of my own work, is just on 3D dust mapping, just because it provides a nice setup where all of these different things kind of come into play. So the idea is that we have some distribution of distances to stars and then some foreground extinction caused by intervening dust. We know that this function has to be strictly monotonic because as we get further away, you only can add dust, you can't subtract it. And so what you expect is that there's some monotonic function that is increasing as a function of distance and is tracing out sort of the total amount of integrated extinction from foreground dust along a particular line of sight. And of course, what we have in terms of observations is stuff that's noisy. So each of these individual points here, you know, has some uncertainty band around it. It could be very complicated. It's possible that we don't even know the uncertainty and we only have samples from some underlying inference algorithm. And we want to use this to essentially learn what's the underlying true distribution of dust along a given line of sight. Using those, we can construct these types of cool maps. This was work that was led by Greg Green a few years ago, using a whole batch of data from Pan-STARRS and Gaia that hopefully we will be able to update as we get more data from Rubin and other big sources. This is showing just a small orbit around the sun, the 3D reconstruction of dust from hundreds of millions of stars. And this is the type of thing that we can leverage with this type of framework. So what is the sort of classic strategy that we could use to do this? I just want to outline kind of some straw man cases and then sort of lead into where we end up with in terms of uncertainty derivation. The first one is we might just add in the errors, right? So in other words, rather than just predicting you know, some baseline result, we might just say we're going to predict f of y given, you know, x and sigma x, right? Or maybe x, sigma x, and sigma y if we have some uncertainty. And that's just equivalent to us adding in a little bit of an error bar here, right? We're saying, look, we're going to pass in our error bars in these points. And if we have a larger error bar in some direction, that means that effectively we're going to be averaging our prediction along this given region or along this given area. And so we probably are going to end up with a slightly different expected value for our prediction if we have a different error bar. So it kind of makes sense, but it's not great, right? It's a little hokey. And in practice, it tends to, I'd say, does it work? Kind of. Is it elegant? Not quite. And you really hope that your model can do this type of extrapolation down to the types of errors that you're looking for. So it doesn't really behave, it's not guaranteed to behave well if you're then applying it to data which has out of distribution measurements for, say, the errors or the uncertainties here. But at least in theory, this might work. So the second option I want to highlight is then, you know, often in astronomy, we sort of say, let's Monte Carlo it then. So instead, I'm going to train some model. You know, in this case, you know, does this make sense? What I'm going to do is I'm just going to train some model, you know, f of y tilde given x tilde, where these are noisy measurements of the data. And then what I'm going to do is I'm just going to draw a bunch of realizations, which I'll call x tilde prime, from, you know, my noise model, which maybe looks like this, you know, something like that. And then I will just, you know, have a bunch of different predictions that'll give me some probability distribution function or PDF. And so that's equivalent to saying, you know, rather than just putting in one, I'm just going to generate a bunch of these, maybe when I train, maybe when I predict, maybe both. And then this will help me, you know, numerically marginalize over the uncertainties. Now, the one thing I want to take away from this talk, you know, minus the SBI++, is does this work? And the emphatic answer is no. You need to be extremely careful when you do this. And I want to outline two ways in which this fails. One is conceptual, and then one is formal. So conceptually, we can ask what happens if we are incorporating errors into a simple regression case. So we can think of chi-square, right? We often define the residual between our results and the prediction divided by our uncertainty, and we square these. What happens if we increase the error bar here? Well, the chi-square value goes down, right? So if we have sigma y go up, then chi-square value goes down, and the impact on the fit decreases. That's great. What happens if we Monte Carlo now? If we imagine that we add in a lot of noise here, and this one maybe doesn't have a lot of noise, and we start to adjust our model relative to this, what's the behavior that we expect will happen? Well, this point, essentially, because the error is so small, it doesn't change the loss at all. It just multiplies it by a constant. So this one will have some, delta y value, and we're just going to multiply it by the number of, samples that we use to Monte Carlo. So if we take an average, this just cancels out. This one, though, now when we make very small changes, the distance between the furthest point and the line now matters a lot in most cases. In most ML cases, we're using a loss function that goes as something squared. Now, if you have a larger error bar, and so therefore you're Monte Carloing a sample that's further away, you become, squared more sensitive to that point. And so what this means in practice is if you have a big error bar and you Monte Carlo a bunch of points and you average over that without doing anything fancy in your loss function, you actually become more sensitive to points with large error bars, not less sensitive, because those very large scatter points will contribute a huge amount to the loss. And therefore, when you average over that, these points on the outskirts will contribute much more than points close to the center as you move this line around, and will dominate the contribution locally for that part of the fit. So conceptually, this actually does not work very well. It has the opposite effect. Points with no measurement uncertainty don't have any change, versus points with large measurement uncertainties actually contribute more, and you are more sensitive to them. So it's the opposite of what you expect from chi-square. Now, the reason behind this, essentially, is because most of the time when we think about a loss function, this is essentially equivalent to some negative log probability in some model that we need to write down. And I'll get to sort of this explicitly in a second. And what happens when we're doing Monte Carlo and we just put it in the loss is we're essentially taking some average over the loss, which is essentially an average of a log probability. But really what we would like to do, if we're really Bayesian, is actually take the log of the average of the probability. And so the key difference here is where that average comes in. So when you Monte Carlo, what you really want to be doing is averaging in probability, not averaging in log probability. And so for most ML applications, if you either train or generate predictions based on just Monte Carloing points, and you're not careful, what you actually have done is overcounted or double counted the uncertainties. And that's because you're averaging kind of in log space and not logging an average of probabilities in linear space. This is a very reasonable fix that you can do, but it is something that I want to bring everyone's attention to, and ultimately forms the baseline of SBI++. So I'll quickly go through the basics of linear regression to outline this model. And then I will try and answer any questions about sort of what this looks like. But this will be a really crash course and mainly for reference. So the idea is that in like a standard linear regression case, you have sort of some set of points. These are drawn from some distribution. You have some prediction for what these points look like with some set of parameters that you care about. This is equivalent to jittering them around a little bit relative to some, central line. And that's going to be your noise process. This epsilon that's going to jitter your points around. It's going to be drawn from some distribution. And so in this case, you add some more scatter in. And if you want to derive what you would do, we can build a model that says the same way that Mickaël showed this DAG for skysurvey. We want to do exactly the same thing and build a DAG for our model and sort of say how we go from our inputs, which is some fixed value we're interested in, some slopes, some true value, some measurement, and back to some output. We want to do the same thing and turn those into a series of probability distributions and assumptions that govern this, which come down to our noise model shown here in blue, and our latent model shown here in orange. And in this case, for most normal cases, we can assume that this is true for most astronomy and most standard regression examples. Okay, so now if we say, the only thing that we're going to do is we're just going to swap this into some latent parameters. If we don't actually know what a particular thing is, the way that we have to do that is that we need to either marginalize over it analytically, which would be full integration, or numerically, which is using things like Monte Carlo. And so if we have some distribution like this is how we write it in sort of Bayes theorem land. And again, the math is not super important other than to recognize that this integral is exactly saying that if we don't know what the real value is, we do know what the noisy value is. We just need to marginalize over every possible real value that could exist given our underlying model. And this term here is what our ML model is really going to be trying to fit. So the idea is that we're trying to learn a machine learning model that covers the true distribution, the true predictions, and the true observables. And we're going to be convolving that with our measurements. And that's what we're going to be comparing to when we look at our data. And if we do that, then you can get much better results. So I'm going to skip over a little bit of what this looks like for X's, because I think the process just is a little bit more involved. But the main idea is that this naturally introduces the main concept I talked about before. So the first thing that this means is that most of the time to do this integral, to actually marginalize over the uncertainties, you need to have a probabilistic machine learning model. Like you can't just predict a point, you need to predict some width so that you can actually have some overlap between your noise distribution and your model. So it's not just something that collapses and none of your samples will ever hit your machine learning model. So adding some intrinsic uncertainty into the model is often necessary on a practical level to make this work. So we go from sort of some prediction of the mean to a general prediction of the probability distribution. We can even make this more complicated by allowing for changes in the probability distribution as well. So maybe it doesn't have to be, for example, strictly normal. We can allow it to be arbitrary. Hopefully this makes sense. And the idea is that we have moved from sort of thinking of a model just in terms of some basic like loss, and we've converted this to be something that actually has a full, probabilistic prediction that we can now start to marginalize over, so that when we actually compute what P is, we're going to be looking at probability of sort of the real data, and probability of sort of the noisy observation, given the real results, and marginalizing over sort of that whole thing. And this process does work. And the way that you can use this is the same Monte Carlo procedure as before, just implemented a little bit differently. In particular, here's an example of what such a loss function might look like in TensorFlow. Again, I don't want to go through the details of what this looks like. The main thing is that which was led by an undergraduate student here at Toronto, Ava, is that you often will need to use these log sum exp operations to deal with the fact that you have log likelihoods that you need to then combine or average over in linear space. And so you need to exponentiate them, take an average with a sum, and then relog them. And this is a numerically stable way to do that. And this is implemented in most sort of machine learning packages. This process also does work. Here is an experiment we ran with simulated data where we added in both outliers and measurement noise. And we tested essentially against a baseline model, which just used standard loss, which is up here on the top. And then these ones, which allow for us to fit some of these extra parameters like the uncertainty. And in this case, we have an outlier model that we also test. And what you can see here is that this is again, same curve as the one shown here on the right for 3 different lines of sight with different, observations connected by these little lines. And what you can see is that in general, we get this big bias and way underestimation of uncertainties coming from just using MSE. And when we actually allow ourselves to fit for all of these free parameters, we are able to deconvolve out that noise and estimate the true underlying distribution in most cases really well, where we have a really high data density. And so you can see here, there are some places where we deviate a little bit, but those are often cases where we have a very, very small amount of data. And we do quite well in most of these cases. So we're in the sort of process of writing this up now. The final thing that leads us to SBI++, which is really the main point of the talk that I want to just end with a couple sort of big pictures, is that rather than just using, say, a standard neural network framework, we can use simulation-based inference, which is designed to actually predict probabilities rather than just values to essentially come up with this probabilistic model entirely non-parametrically. And this works really well. And the lead paper here that I encourage everyone to take a look at was led by Bingzia Wang, who's a postdoc at Penn State, along with Joel and Ashley, who co-chairs the ISSC and helps to organize these seminars with Francois. And then I'm there because I help to contribute to the methods that I talked about here. And I've been working a little bit on some of this with an undergraduate, Yihan Wang, here at Toronto. But the main thing, the takeaway, is that there are lots of different ways to think about how to incorporate uncertainties, measurement uncertainties into this. And Bingzia's work has shown really well that we can extrapolate to out-of-distribution measurement errors really clearly. This is the result from testing on sort of mock JWST data. And the key takeaway from this corner plot is essentially the result from the dark and light blue, which is comparing nested sampling and SBI++, which incorporates this marginalization process, with the result where we just apply a naive method trained on this high signal-to-noise bias data. And you get to see this very clearly, where if you just apply it, noise your data to a model that is trained on, out-of-distribution results, you get results that do not look very good. And you get really good agreement actually between these two methods once you accommodate that sort of extra noise extension. And this isn't anything controversial, so hopefully this all makes sense. And I had some nice pictures, I guess, as well, which I forgot about. You can also do the same thing to do with missing data. You just essentially extend that marginalization to be from -infinity to infinity. And we come up with a very crude approach to do this using some neighbor search. And again, we find like very good agreement between the two methods. That we are able to effectively marginalize over this, and that allows us to extend sort of these approaches to work with both data that's out of distribution because it's noisy, and also out of distribution because we're missing a band or two. This also really does successfully deconvolve lots of noise. So this was work led by Zichang Sun, which was accepted to the NeurIPS sort of machine learning for physical sciences workshop coming up in like a week and a half-ish. And here's just him showing that we can put in very noisy observations and recover the underlying population distributions relatively well, even with priors that we know are misspecified, which in this case are just flat. So this actually does work really well at really doing what we want, which is to take that measurement noise and learn sort of the true underlying distribution. And once we have that, we can then extrapolate to other types of data. I'll skip this last one, and I'll just end with sort of the summary about what the main takeaways are, which is going from this sort of basic picture to a probabilistic one, really has a bunch of wonderful effects about trying to deconvolve data and uncover distributions, and also does really well in extensions to sort of these types of, and I'd say, real astrophysical settings. So hopefully this is at least a good introduction to how to think about these things. And if you have any questions or are interested in sort of the package and framework, also Bingzia has some code up online that sort of implements some of these, which you're welcome to check out. So that's it for me. Hopefully, yeah, I'm happy to take questions.
Thank you so much, Josh. Very nice talk. And I already see a few hands up. Casey, do you have a question?
Hi, thanks for your talk. I just had a question. You kept saying out of distribution errors from out of distribution data. Which distribution are you out of? I wasn't clear on that.
Okay, good point. So the out of distribution is that you are out of distribution in terms of conditioning on the measurement uncertainties. So you're sort of extending from a data set conditioned on one population of measurement uncertainties to a data set which maybe has the same underlying parameters or population distribution, but different measurement uncertainties will give different sort of realizations of the actual measured values. So in that case, you're out of distribution because you're conditioned, the distribution you've conditioned on, which was on some range of uncertainties, has been extended to a different range of uncertainties.
Oh, so you mean you're like applying your machine learning model to a test set or a held out set, which has different noise properties than the one you trained on?
Exactly. So different noise properties is sort of our key metric here. Yeah. So often much lower signal to noise. Okay, great. Since I don't see any other hands up, may I just ask another question? Relating to what I just talked to you about in Banff, actually. So
in the case of linear regression, Brandon Kelly did this well-cited paper about how to deal with, at least in the linear case, linear regression, Gaussian uncertainties on both the targets and the inputs.
Yes.
So I suppose what you've done is extend that idea to more nonlinear machine learning methods. But one of the key insights I learned from reading that paper is that when you're dealing with uncertainties on the inputs, so the X values, it's a bit trickier than on the Y values, because when you're doing regression, either linear or nonlinear, you're looking at P of Y given X. And if you have, say, Gaussian measurement errors, Y goes above and below the expected value equally. But when you're talking about the X values, if you imagine the distribution without the errors, when you say it's like that, and then you add the errors, it broadens, and you get a phenomenon called regression dilution, where if it was linear, your effective slope gets decreased.
Exactly.
And so to correct for that, you actually need to assume some kind of prior that you might need to fit for, which would actually bring those X values back to the center.
Yes.
Which is tricky. So I guess in a general case like this, it's not obvious what you would do with the prior on the X-axis. Like, is it physically motivated, or is it just a mixture model, or what's the right thing to do?
This is a lovely question. In the sense that, so I think Brandon Kelly's work is exactly the type of thing that we're trying to build on in sort of this much more general case, thinking of the same techniques. It has exactly the same drawbacks. So you get this interaction between uncertainties on the X-axis now propagating to uncertainties on the Y predictors based on the exact, in this case, non-parametric model. So it's not like you can do sort of, simple Taylor expansion. You get some kind of gradient, and then you multiply that by the uncertainty on the X. In this case, you get some very nonlinear averaging process, which makes that much more difficult. And one of the conclusions that comes out is we do need to have a prior over the actual population, underlying population in the data space, like the true distribution of those data values. And in most cases, in most of the applications that we've done so far, we have assumed that that distribution is, either something very easy, like just Gaussian, or flat. Uniform over, some bounds. And what we have found in practice is that as long as you have, depending on how good type of relationship is, it does look like you can recover a lot of the underlying structure, even with priors that we know are pretty misspecified. And in this case, for instance, actually, if you zoom in really closely, let me see if I can actually do this here. Yeah, if you zoom in on kind of this region here, you can actually see that because our prior is broader, we are actually failing to recover all of this exact substructure in this sort of crescent moons example. And so that's why the red is actually slightly broadened relative to the blue. It's actually because our prior is on all ends kind of a little bit too flat. But that's one thing where I believe that the strategy that I'm interested in looking into is whether we can sort of simultaneously or jointly train another type of non-parametric density estimator to try and come up with something like this. But it is one of the sort of next steps here, is that we currently have not been running this with sort of the full correct prior implementation for most of these cases. Yeah, so excellent question.
It gets better every time I ask it.
Thanks for the question. I think, Mickaël, you had a question?
It was part of the discussion. So we are actually, I am still in the attempt to fit lines that have errors in both directions. And actually the solution we end up with was not something that includes a prior on the X-axis terms. It was actually, we had to fit for all the true parameters. And so for instance, if we want to fit for, I don't know, X equal A times X, I mean, basically a combination of linear terms, we fit for every true parameters, knowing that I'm assuming that my errors are perfect. And I know them. But if we do that, then we just need to, I mean, if we want to fit for 3 points, for instance, it's a sum of 3 linear relations, like a standardization of 1A, then it means that I have to fit for 3 times the number of observables I have for just 3 parameters, which could be quite a lot. I mean, at the end, I have a sample of 1,000 supernovae. I'm fitting for 3,000 true parameters that I'm going to trash anyway at the end. But actually, it works now. And I'm able to do that in the fit quite easily with JAX nowadays. And so I was just wondering what was the difference between trying to inject priors and stuff and trying to fit for the true parameters.
Right, so they're the same thing actually, because when you're fitting for the true parameters, that inference does require a prior, either implicitly or explicitly. And so that's sort of the same thing that Casey's saying, is that if you are trying to fit for all the true parameters, then there is a prior that's put in there somewhere. Either you have a conditional distribution for like y given x, which is the case in linear regression, but then there has to be something for x if you don't have a relationship over that. So the prior kind of comes in there. And either if you haven't specified a prior, then you're assuming it's flat. And if you have, then you sort of get different behaviors, and it does impact your results because you need to engage in some shrinkage. And the main thing that's coming up here is in most ML models, in theory, you can fit for a lot of parameters. I mean, many models are getting to be huge and you can optimize them. But it's a different sort of story to optimize the parameters of your model and also solve for all the true parameters of the data. And so what we're sort of proposing here is a framework where you can marginalize over those unknown true parameters at every step of the algorithm. So that every time you compute sort of an effective loss, what you've done is you've sort of marginalized over all true values of every data point, and then you use that to sort of decide the next step for optimizing your machine learning model. Hopefully that roughly answers your question.
Yeah, thanks.
Right. And we have 1 minute left, so I don't know if there is one pressing question. If not, thanks again both to Josh and Mickaël. And Josh, if you can send us your slides, we'll also join them with the link to the recording and everything.
Absolutely.
At the end of the session. Thank you both, and thank you everyone. And
Very much.
see you next time.